Okay, so here's the solution for number 65 from the Calc BC Final Exam Review. It takes a little bit of kind of reading it and seeing, maybe drawing a picture, which is what I did, and I do apologize for the quality or lack of quality of the the picture and the writing here. I need to get a better writing tool with my mouse. I'm trying to do all this using the computer because it's really hard to sit. I can't sit right now, so I can't really sit and do the videos. I'm laying down trying to do this using my mouse and the screen capture. Anyway, hopefully you can just bear with me here and get the concept and get the most important part of what you need here. After looking at number 65, it's actually not that bad. It's a very good problem to look at, to remind you of the connection between finding area using integrals, where we first found area using, we found the approximate area using the Riemann sums, and applying the Riemann sums to volume, we can, this is a good example of doing that. Finding volumes of cross sections, a limited number of cross section volumes, and then we can approximate the volume of the entire region, or figure, which is what this problem is asking you to do. And so I found the volume of the first cross section, and then there's very little work to do after that when you see the pattern. So the blue curve represents the graph of, let me get that in here, is y equals the square root of x. So it says we're taking this region here in the xy plane, revolving around the x-axis from x equals 0 to x equals 6, and we'll have a figure, three-dimensional figure, and we're trying to estimate the volume. And by partitioning it into six subintervals. Sorry, I guess I can't write on that. Of equal length. So anyway, I drew the first few cross sections. You could draw the next few if you like to. I didn't need to do that. Just wanted to show you. The first cross section has a volume. Remember, the volume of any cross section is the area of the face. If they're discs, which is what these are, area of the face multiplied by the thickness of the disc. Okay, well, the area of the face, of a circular face, which you can see when you revolve a region around a line, you're going to get, there's no gaps in there, so you're going to get discs, and the face will be a circle. So the area of the circle is pi r squared, the thickness is our dx. This particular face, the radius happens to be the distance between the x-axis and where this disk actually hits the curve. And let me try a different color here. So this particular radius is right here, and as you notice, on the x-axis, it's halfway, it's in the middle of, I should say, the first subinterval. First subinterval goes from 0 to 1, and so halfway is 1/2, and the height then of the disk, which is the radius of the disk, would be the square root of 1/2. Okay, which is where this comes from, the square root of 1/2. And again, pi r squared, r being the square root of 1/2, you square the square root, and you just get the 1/2. Where does this 1 come from? Well, the 1 comes from where it says the cylinders have height 1, and so that's the thickness of that particular cylinder. And it's just the thickness of that subinterval, or the length of the subinterval. And so, all in all we get here is that the volume of the first cross section is pi times 1/2. In other words, pi times the x-coordinate right there. All right, so that really makes it easy to find the approximation for the total volume. So we have the volume, so I'll give you the pattern, you can do the rest. The volume of the first cross section okay, which is pi times 1/2. We're going to add to that the volume of the second cross-section. So here's a little rationale here. The thickness of each of these cross-section slices is going to be 1. So the thickness is always going to be 1. The pi is always going to be in there. The only thing that changes with each of these cross-sections is the radius of the cross-section. And as you notice, there's 6 cross-sections, and the height of each of these is then just the next halfway point between on the interval. And the halfway point between 1 and 2 is 3/2. So the radius of the second cross-section is the square root of 3/2, and then when we square that, we're just going to get 3/2. So we can see a pattern here. Let's see if we can even factor out some things and make it even easier to find this the easiest way possible. Pi times 3/2, radical 3/2 squared, which is just 3/2, and then we have pi times. So now the pattern starts developing. See, oh, that's pi times radical 5/2 squared times 1 plus dot, dot, dot. This is really, really hard, sorry. And then, so that's equal to, if we factor out a pi, in fact, let's factor out a pi over 2 from each term. And if we factor out a pi over 2 from each term, then we're left with 1 plus 3 plus 5. Oh, this is good stuff. This makes it really easy. Some of you are watching this going, oh man, I added all those fractions. I wasted my time. Plus 7 plus 9. How many do we have? We have 6, right? And then 5. Yeah, that's 11/2. 1, 2, 3, 4, 5. And then 11. All right. So there we go. Now what do we have here? 7 and 3, that's 10. 9 and 1 is 10. So we have 10. So let's check this out. Let's make it really fancy. So now you just want things to be fancy. Let's see. 1 and 9 make 10. Of course, 11 and 9 make 20 anyway. 3 and 7 make 10. So we have 10, 20, 31, 36 over 2 is 18. So we have, let's put it in blue, 18 pi. 18 pi. And which one is that? Well, I don't know if that's the A or if that's the C. So 18 pi is 56.5487, and that is A. All right, it's kind of fun when you get these right. You know that's got to be the right answer. There you go.